And welcome back to another episode here at Rottler Manufacturing at the Engine Performance Expo Live 2025. I'm Ryan, and I'm here once again with my old friend, Randy Neal. Randy, how we doing today?
Buddy, we were having a ball. One thing I've had the opportunity to observe some of the previous speakers, Darren, Keith, Ed, Mark, God, what talent. You have really brought the best of this deal. And then, of course, I get to work with the superstar, Ryan.
You're too kind.
There you go.
Well, Randy, I mean, balancing CWT, crankshafts, harmonics, parasitic losses, the whole nine, that's your spiel. It's been the stick for a while, and it's always enjoyable to listen to what you're cooking up and working on. You know, I think from my side, kind of in just the fundamentals of engineering and physics and my limited understanding of those things, I think there's, when we look at engines and, how we optimize performance, and it depends on our application, depends on what we're trying to achieve. But I think, for me, sometimes we get it confused. It's very easy to think if I'm going to make a lot of power, then it's a trade-off. I can't have an engine that lasts long or vice versa, right? But in engineering, you look at stuff as, what's your two biggest losses to anything you're trying to optimize? It's things leave the system, usually in heat and noise. And we can look at some fundamental physics that happen and crankshafts, balance. That's what we're trying to look at these things. Anytime we have a dynamic system, we're going to have movement, we're going to have friction, or we're trying to get rid of friction. It just doesn't matter, to me, whether we want to make more power or we want to make something that lasts longer. We need to be taking a structured approach and trying to think about the systems we're working with, I think, a little bit differently. So.
Well, listen, you've actually sort of outlined pretty well. One of the things that we are able as engine builders, we've run into an era now that we can make power fairly easy. It's very interesting how this thing in a very short period of time has evolved. In fact, just a real quick picture. I'm just going to show you a couple of different applications of how you guys are making power now. And this is just a quick overview, but the key is there's no one set path. And as we go into that, what we found, especially with these guys here, they're more entertainment horsepower than anything else. But at the end of the day, understanding how power affects physical resistance. And what I mean by that is, whatever the material is, I don't care. And we're going to sort of focus on cranks a little bit here. But as we make power, it will only take so much until it doesn't. Now, that's complete failure. But along that path, it goes through a distortion. And it is linked in so many different areas. I know, like when Mark is sitting there talking about surface finishes and so forth and geometry, most of the time we measure that in what we can consider a rested state. Well, the engine doesn't know about that. So as soon as we make power, game over. Different environment. And so the key is we're at a level now where we can make so much power so easily. We're still using the fundamental principles that we had before. These, pistons go up and down, cranks go round and round. Not the same stress factor.
That's in Mark's presentation earlier today, and we were talking about, I was asking those same questions, right? I mean, you're measuring something in a static state. And the way we go about measuring things, the conversations being what devices, what tools, and everything has assumptions, right? So we make assumptions even sometimes when we don't think about it. And the important thing is to understand the assumptions so that we know, in my opinion, if we're doing the right thing or going down the right path and getting accurate data back.
Yeah. Well, listen, that links into a single word with me a lot of times, and it's called Voodoo. In other words, a lot of engine building that we've done are practices as opposed to a science. In other words, we come up with this idea, and I always enjoyed the market because as soon as I tell a guy he can't do it, his next comment is, hold my beer. He's off to the races with this thing. And then we get on the other side and start studying it and finding out, hey, how much is power made against power applied? So then we start doing a deep dive into parasitic loss. All of these things with distortion, drag, however you want to define it, become hidden enemies of performance. So we'd like to understand, especially in the balancing community, again, I'm back to that Voodoo world. It's always been a science since day one. The hardware that we had, a little weak, right? So a lot of times people would guess, and as they would lead into process, they would make up, well, let's just say unique profiles. Well, the original machine was actually built in 1883, and that thing was an absolute albatross. However, it was at least equal in function as the current status. The difference is how you interpret the data. Well, it used to be it was all here. Well, now because of technology, and I'm watching what you have done here with Rottler, we've actually been able to take and harness that and put it into a platform that we can now read, see, and respond to that we never had before. So software, yeah, that's good. Well, you know, when I look at what you guys have accomplished and how we're headed, well, we're going to talk about it a little bit. We'll dive into that a little later. But let me just move on here for a second, because here we are. When we don't understand what's going on, we call it harmonics. Now, there is the link to Voodoo, if there ever was a simple word. Now, harmonics actually is a traceable dynamic. We can measure that. We have a multitude of ways of getting it, and there's different applications. So let me just give you a little idea. Now, this is just a quick visual of how we could generate a frequency of intercept with two different objects. Although they are based in the same frequency, I just want you to take notice of how this works. So here we have two tuning forks. One of them on the left, of course, in the picture, has got two little attachments that we can modify that frequency. But watch what happens. Now he is struck, and you see the response by that ping pong ball. There's air between it. That's the only contact. That's the only way it's linked. But interesting enough, now we're going to go ahead and damp that. And now he's going to change the frequency that's generated from the mechanical excitation. What's interesting is not a big frequency difference, but it's totally unique. So now what he's done, you see nothing, nada. What's important to understand is that, especially mechanical devices, have natural frequencies, all right? If you give it a catalyst or a stimulus, in this case, he struck it, what do you think's happening when we make combustion? We don't just doing it once like he did. This thing is relative to sequence and then RPM multiplier. In other words, the rate goes up. Well, we often talk about frequency intercept, and all I can tell you is the only thing I know to do when you find it is get out of it. You cannot take a single area, and although we do, and we'll talk about this a little more about damping, but it's not universal across the board. It's limited by frequency intercept. So as we move with this, there it goes. I want to give you some idea what happens, what you just saw though. You're visually seeing a sinusoidal wave generator on the left, but you notice this little red line right here. Well, I'm going to link over here, and what happened is here's a critical frequency intercept, all right? Now this is pretty easy to follow. This is basically represent rotation. All right, good. So what I'm going to do now is I'm going to invoke a multitude of frequencies, and you can see this, there's these oscillations, but look what happened to my previous perfect sinusoidal wave. It's been disrupted. Now, if you attach that to the mechanical activity, and let's just go to the camshaft for a minute, and it's simple, I have a follower, right? And it's meant to be, well, the engineer who's designed the profile, Billy Godbolt, has designed this perfect cam. And so you have this following device. It can be disrupted by harmonics.
So I just want to touch in a couple questions here. I mean, the tuning fork thing's perfect, right? And you go, well, what's noise? What's all this stuff? It's and I know from school, it's a pressure disturbance. It travels through, and you can, like as you said, every object has its natural frequency. So this is interesting because I don't think. I didn't even think about this until you showed me this. And the reality is we're all looking at these plots that are perfect sine waves. They're all over the world. I could talk about the same stuff in end mills or in tuning motors, anything that spins, ball screws on machines. This is all the same stuff. And we always map them or tune systems in assuming we've got a perfect, or all our examples, all our theoretical stuff that's what we're trying to achieve. But the real world is not that. There's noise. I mean, whether we're doing, waviness versus surface roughness, all the conversations we've had, there's this theme that I'm learning here today is, everything is a very messy looking sine wave, and there's all this noise, right? But that's a different approach to thinking. I mean, I kind of like what you touched on earlier that, and Darren was talking about it. Mm-hmm. He's got the same thing. He he's looking at the signal and
Yep.
the harmonics inside of an intake manifold.
Yep.
And, you've got harmonics happening in a crankshaft, and you've got a piston going out. So it's all over this engine.
Right.
But we were talking about it with Mark specifically. It's so easy. I do it. We've all done it. It's so easy to look at one single component, look at it statically, look at these
Right.
things. Is this a thing that you're seeing and from time in the game that this is a different way of thinking or paying attention to things that maybe we haven't looked at, or we knew it was there but we couldn't measure it before?
Well, you hit on 2 key points. Measurement. The old saying simply said, if you can't measure, you don't know. All right. So I can mechanically illustrate what's going on, but then we have this event, right? And sometimes it's not singular, but more importantly, it's transient. All right, so we can have I'll pick on a single frequency, but it's not a one-time hit and go home. But as we go through over time, we'll actually have a redundancy of that. Well, guess what? Then we have this other guy coming along, and then you have chaos. All right, so one of the things I would mention is that we try to find a means of damping that. All right. Sometimes we can do it electronically, sometimes we can do it in software, but can we absolutely harness it? Not if it's a variable. Once I have known frequency, I can go ahead and find an opposing event and cancel, right? Guess what? This engine doesn't care to hear that. And let me just bring this up here real quick. When we sit there and we run an engine, there we go. Basically, you got to understand, as this thing is going through its normal function, look at all the components that are interacting with each other. Each and every one of them has its own natural frequency. So we can bang on one area in RPM or load and create an event of excitation, only to be canceled within the next 10 RPM or 5 RPM, sometimes 1 RPM. So it's in and out, in and out, in and out. Now, the problem is, where I'm trying to go with this is, we don't know what we don't know, but only through achievement of technology are we able to now come up with diagnostic equipment that can go in and sample, report, and then our mission is to sit there and say, how do we counter this? So if I compared engines, and I'm talking about from an OEM street car to a Formula One, that's not apples and oranges. That is planets apart, right? So when we have people trying to link that as a common denominator, the only thing I'll say that's common is the word harmonic, right? The specifics of each engine has its own, what I call, a personality. Well, as we build different power, and that's one of the things these guys are really good at, let's be fair about it. When we have a normal combustion cycle and at a fixed RPM, I can profile that and I can probably identify the offending issue. All right, let's go ahead and increase the compression next time. Or let's change even the fuel. Just the fuel itself changes the entire concussion event, which is taken by combustion. And these units will respond differently. I used to sit there and tell people that if you ever have the opportunity to really do a deep dive and see what happens in a combustion chamber, you'll never get in another engine again. It'd scare the hell out of you. The first time I had the opportunity to work with Ford directly and learn about seeing visual flame propagation. And the guy told me at the time, he says, well, we're going to go to lunch. We have X hours. This thing's going to blow up at about 12:35. We'll get here at 12:20. I said, what? You're crazy. And we went to lunch, and I'm setting this guy up. I'm going to hammer him. Guess what blew up? On time. So he knew in the profile, and this wasn't a simple deal, but by understanding the event, you know what happens with a limit of capabilities mechanically that it can sustain the load over a period of time. We don't have that in the race community. We're cowboys. I'll put it as blunt as I can get, and that's what makes it fun. Sometimes I'll go back to Top Fuel and I keep looking at all the power to get, but that's not why people watch them. They want to see the explosion. That's their entertainment factor. Well, I'm on the other side. I'm a durability guy. I want to be more in the Formula One dynamic philosophy or Cup. Let's be fair about it. It's not that the Cup guys are making horrendous horsepower, but they made it live, at least for 500 miles, right?
So there's I can't remember. I think it was probably a decade ago, someone told me, they were like, just on the Formula One thing or in that world, in that scenario, I mean, the ideal engine, if we're looking for applications, an ideal engine would explode right when it got across the finish line. Hopefully won the race. But, just on the Formula One thing, kind of what we were talking about, right now, the current engines, in that world,
Sure.
some of the most thermodynamically efficient engines ever designed, and they're making 1,000 horsepower, and they're also lasting. So, I mean, and they're doing hybrid stuff. It's not all pertinent, but do you see in what you've seen with your experience and this playing around, that if you're understanding some of these dynamics, some of these harmonics things, that you're able to get more power as well as increased longevity? Or
That's the goal.
yeah.
Ultimately, I don't care what people want to do. I mean, blowing things up, what'd you learn out of that? You learn how to blow shit up. Where's that going? The key is to find a way to make it make power and sustain life. The performance guys as a whole are inquisitive, but fortunately, we're doing like presentations here. We're starting to get them to have an awareness. Hey, you need to know how to measure what's going on. You need to know, if you don't have that data, you're guessing. Guessing is not a good business model. You know, you need to have understanding of process, and more importantly, if you understand it, then you can get a known result plus improvement. But if you put the question mark at that equation, and I guess the best thing to do is go to church, because I don't know about an answer.
Yeah, something about the technology side too. So, one of the things that's always interesting to me, and I liked the way Darren put it earlier. He said that, a lot of the stuff that he looks at, or a lot of how he's learned and honed his craft, was looking at things from the 1930s, Rolls-Royce Merlin engines, old NACA, discussions, stuff like that. And I'm always, the engineer in me is you typically see these technologies, and my conversations with Mark, it's a great example. It's, you could spend $10,000 or $15,000 to measure waviness. You could spend $450,000. Have you seen? I think one of the interesting things is seeing how the curve of the price of technology, the cost of technology, it allows more people to access it, a lower barrier to entry, right? But as that changes and you have access to that, it allows you to do more things. It is actually proven, but you have to often change your thinking. I mean, it's easy to say, well, this is the way we've always done it, and I think there's a paradigm to do that.
Well, actually, it's sort of interesting. I'm going to use Darren because he's a very knowledgeable guy. He thinks so far out of the box. I'm amazed. But he hit on a couple of things that he says, wait a minute, let's go back and look at a few things that has happened. Can we learn from that? And can we now introduce that with, well, quite frankly, the ability to measure? I think of Mark also as a guy, he's been trained at such a level in the OE, he is really about durability. This thing has to last. But he has to know what he's looking at. He needs to know how to massage the data. That's an important part. So let me just bounce off this and sort of key onto this for a second. I just showed you a rotating issue, but here's what's causing a lot of this excitation, and it's called torsional load. That torsional load that you're seeing is just depicted here on the screen. So just think about walking out on a diving board, and we've all done this at some point in time, and you notice as you get farther and farther away from support, the spring rate changes. Well, as you change stroke or rod length and everything, this changes the characteristic of excitation. Material is important. Machinability of that is also important, by the way. In other words, it can't just be an alloy. It has to be an alloy that is structured. We see all sorts of different types, aluminum rods, steel rods, all different configurations, but they all have their natural frequency. So let me bounce into that real quick. For instance, the ProMod guys, right? They're very, once again, a great group, but they have learned how to commit financial suicide on the burnouts. Now, what that means is they'll sit there and they'll run this long burnout at a known frequency. Now, the driver's just having fun, right? But I guarantee you, if it makes it to the other end without blowing up, they've learned to take it back and change bullets. They know that they've heard it, but they just got lucky. Now, how did that happen? It hit a natural frequency that it took this incredibly perfect alloy and turned it into a soft material, all within the burnout. Top fuel, same thing. There's a lot of guys that have learned, and I'll talk about fasteners for a second. Understand how the fastener intercepts with the capture point, how that does respond to the excitation or the strength of that connecting rod. So these are all contributors to longevity. The power making's topping up. Keith's got a great example about the importance of sealing that unit through geometry and materials. Okay, I'm on the other side of that thing. I just want it to live. Well, as soon as I hit a natural frequency and I stay in that zone, I'm going to tell you the material will change its integrity, which is to say it's not going to be as strong as it was. We're learning that more and more. The tuners, right, the crew chiefs, they're starting to step up. They're realizing blowing up an engine is not profitable. So they want to come back and say, we got to win the race, rule number one. But number two, we want to make the next round. So they're learning to get better. We're going to show this a little bit more when we talk a little bit more in depth with cranks. But let me spin off just a little more here. One of the things I'm going to show you in this pictorial, I'm just showing a single cycle of rotation. But if you guys can see on that chart, you're going to see a red, green, and then even a magenta line. Now, just to give you some perspective, the red and the green are basically relative to surface speed of the piston. Okay? Now, you notice there's a slight difference there, and if you look at the very bottom, you can see two different forms. One is almost perfect bead, the other one's sort of a U shape. Same rod, every other cycle is doing that. But that magenta line right there, that's called a second order, right? What happens is it's introduced because either the difference in surface speed, rod length, angle, a whole bunch of contributing factors, and that introduces itself to this second order vibration. Flat plane cranks, Formula One's known for this kind of stuff on some of the stuff they do, but let's simply say that even the OEs, Ford, General Motors, they took a shot at this also. So I want to give you an example here. This is actually the flat plane unit from an LT6, right? Everybody loves a flat plane because it sounds cool, right? The induction side of that equation against a conventional cross-plane engine, apples and oranges. And Darren would be the guy who could really tune me up on that. But let me go back and still show you the same thing that takes place here. Again, you're looking first at the red line, or you might even think of it magenta, and then the blue line. Well, those are the mechanical speeds that are being changed as this engine's running. But notice the green line. In other words, there's a double hump as opposed to a single-sinusoidal wave. All right, now this is GM's, but now I'm going to take over to Ford. They call it the Voodoo series. What was different in these two engines was one was bore over stroke and the other was stroke over bore. Okay? So it changes the entire characteristic, and I want to pay attention here to the bottom and what you're seeing right in this area here, and you're going to see another hump, right? Now, what's interesting about that, on the Voodoo units, what they did was they were tearing the alternator completely off the car. So they come back and build this massive, ugly-looking mount. Then they're dropping oil filters. Oil pumps are breaking off. And I keep telling people, if they stayed with this, eventually the dashboard will fall out. This harmonic goes all the way through, and believe it or not, that gets so far in depth, it will actually attack the ring and pinion gear. In other words, we'll see fretting that we see in some of the applications we have. You'll see fretting on the ring and pinion, all caused by that second order. So it's an amazing hostile environment, but it's frequency-based.
So if I understand this, you're getting a second order vibration on this, but I guess the question is, now going back to that original, you've got your sinusoid. This would
Sure, we back up.
Is this going to affect that? Is that what was going to cause where you're going to have an imperfect sinusoidal?
You have
line,
another
correct?
exciter in the process of rotation. I'm using the word exciter as a simulator, however you want to define it. Remember the mechanical activity, that's a nice sinusoidal wave. Looks cool. All right. We do know that surface speeds change, and this is go back to Darren because he'll pick up on that because this will introduce especially on normally aspirated, it changes the entire initial induction signal. Well, that's why flat plane and cross plane, man, and when I hear about porters talking about this and calling them the same, they missed the boat. Go ahead.
So if you're, back to, just to key in on Darren there, he had a very nice way of, a slide. Here's what I'm looking for, the application, how he's going to approach designing the ports and the manifolds and what he's looking for.
Sure.
Are you seeing, and his comment was, he goes, I look at what components are going into this engine, what's been purchased, and then I'll design around it because this is going to tell me and dictate what I need to do. Are you seeing anything with this type of information where people are looking to understand this to then design around the application to avoid or
Well, let's do it this way. I'm going to go back to the single differential between cross-plane and flat plane. He would be the one that can really pick up on that and say, look, you don't treat the two the same. They're different animals. And in fact, people who are naive to that process fall in that trap every time. Person of his scale, he knows. He knows where to get. But this is data in. This is where I'm going with this. As long as you have numbers that are valid, what is it? If you can't measure it, it doesn't exist, or it shouldn't be playing with it. Everybody in here, Mark and so forth, data is king, right? But now we know we have a stimulator. Now, interesting enough, if I go ahead and I vibrate enough, I can take the entire characteristic of the camshaft profile and disrupt it violently. Now, we talk about lofting and everything in camshafts. Okay, that's assuming that here's the example. I'm driving on the road, superhighway, just been paved, life is good. I run off the road a little bit, one wheel. As soon as that thing sees an environment change, then you're going to feel it in the steering wheel instantly, even though it has to go through all this mechanism. But it is that fast, right? Well, that's a frequency intercept right there. You've changed the spring suspension, and all of a sudden it's reacting. Well, it's sending in a harmonic event that causes mechanical disruption. So you think about that and sort of leapfrog that into we all know how camshafts work and following work. Well, if you can create that here, you can create it there. If I excite a natural frequency, it basically goes, I don't want to call it hysterical, but I'm going to use the term hysteresis because it's lagging, but it's nanosecond lag, okay? So it disrupts the profile of design, which AKA kills horsepower. And breaks stuff, to be honest with you. You get too hostile here, Valvetrain gets really, really upset, okay? Best example I can use there is if you take a pro stock motor, right, 500 cubic inch. I just chop it right down the middle, same cam, same valve, same everything. There's 1/2 motor. You get just above about 7,500 and you're going to start chunking parts. But yet, when you put it in a B configuration, you're 10,000 RPM. Same part. But the difference is what we consider a flat plane environment with accelerated aggravation in this particular case, a second wave that is generated, not compensated. So all of a sudden, the Valvetrain goes stupid. So there are, do I think people totally understand that? A few do. But I had this discussion with Billy Godbold a long time ago, and he just simply says, you don't see what you can't see. So, but now we're starting to learn how to measure. Well, that's the evolution of industry right now. The ability to have hardware and technology that makes a difference. So let me just go ahead.
Yeah, so I mean, natural frequencies, yeah.
There you go.
Natural frequencies, you're going to have, I like what you hit on. It's well known and understood, I think, that if you excite anything really in the world, piece of equipment, any part, at its dynamic, at its natural frequency or a mode of that it behaves not to the material properties that you're probably expecting, right? And you can have these things can turn into spaghetti.
Yeah.
So, I mean, is that, I know you got some good stuff here, but talk to me a little bit about that. I mean, is that...
Well, this is actually what I'm leading into. You're seeing a torsional event, out of all things, in a flat plane, so it's a double whammy. In other words, the torsion, if you take a piece of metal and you start loading, unloading, it's not going to be like it was virgin. It's going to change. I don't care what you've done to it, it will change under this kind of activity. In other words, all metals have a certain yield life, and then they start to cover. Aluminum goes like this and dives. Steels, for the most part, they just sort of gradually, but they sort of plateau at a given point. In this particular case, we're solving this in a flat plane, and that's what I'm trying to say. I'm giving you a visual real quick. I'm hoping it links with what I just said, but what happens when we do a cross plane? Well, here's an FEA of it, and the thing I want you to sort of pay attention to was we do this by the color code on the left, and where we're having indications of pressure. One thing I want you to notice, I'm going to freeze frame this for a second, and I want you to take notice the hardest, what I consider the most aggravated part on the crank is what? The counterweight. Now,
the red areas.
Yeah, look at this thing. Now, you see the load on the journal, but here's an interesting thing. John Kazi, who's a good friend, known him for 40 plus years, he builds a lot of big mountain motors, all right? And so he is sitting there, and I asked him, I said, what kind of lateral event are you seeing here? He said, front to rear, we have seen as much as 200,000 spread.
200,000.
200,000. In other words, you're seeing
a
the
quarter
witness
inch.
mark. Per inch? Yeah, no.
It's a quarter inch.
Yeah.
As near as makes no difference.
Well,
That much?
it shouldn't work. This thing should blow up. Well, eventually it does. All right? And this is what I'm saying. Power emitted against an object, it can only withstand so much load. Something has to surrender. Now, here's the interesting part about this and balancing, because I want to call this in, bring this in full circle. That counterweight is the one thing that's more, well, let's just put it on, it's mad. All right? Now, interesting enough, the primary principle of the counterweight is to be a counteracting weight against the piston rod mass assembly. All right? That's the primary. But it also is a damping device by its mass. Okay? Well, then we add to the fact that it now has distortion. So it would be nice to say in frequency. In other words, if I said 100 hertz, I would know exactly what that RPM would be. As this goes on, and that 100 hertz would be sequential. In other words, I could follow it. When we get this, now we have a new additive, flutter. It's not linked one-to-one. In other words, it's a total renegade input. Now, all of a sudden, we're seeing excitation in such a different way. So in the old days, what people would do typically is drill the crank, number one. So I started barking about this about a decade ago, and I simply said, you do realize you're changing the strength of the counterweight. They said, you don't understand counterweights. Counterweight, by implication of the name, is to counterbalance. Okay, but it's not singular to that function. So we have changed that, because now I'm just going to skip here. If you see this, let me tell you what the bearing sees. All right? Remember, this crank is flexing, and it's supposed to be within the scope of oil film, journal, and bearing. Look at the picture here. Look at this diagonal representation here of distortion of the crank. And that's all it's doing, is testifying to us that this thing is not what we would consider single-cycled. It's going through oscillation, right?
Yeah, and I really like this. I mean, we were talking earlier about looking at failure modes and wear with gaskets, cylinder head surface, the block deck surface, and using that. And this is a great example of just that, looking at these things. So you can see this, and well, I mean, half the bearing looks new still, so.
Well, you can look on one side of the bearing, it looks like it's right out of the box, right? And then you look at this other, and then look at the one on the left, and you see it's diagonal. Now, that's interesting, because what that's telling you is the main is moving. It's not staying still, all right? It's actually distorting, but not what you would think this way. It's actually distorted this way. It's skewed. Well, that's what happened with power. We've all seen bearings. A lot of times we'll see situations where we will actually see on what we call edge wiping, and that's because it's cupping, right? Or it could be that the radius is too big or something like that. But here's what happens. From this next process, you end up with this problem. In other words, you're right into the radius area, and this is generated by excess power. Just think of it as twist. And if we talk about, for instance, like a Pro Stock engine, there's 2.5 degrees lag at peak RPM, peak torque, between front of the motor and the back of the motor. Now, we want perfect 180s, but it's really got a 2 to 2.5 degree lag, and it changes depending upon resistance. So all of this that's taking place does have a controlling agent, and that is called a damper. All right, now, damper's primary mission is to, I would love to use the word sequester, in other words, get rid of, but it is a damper, meaning it's going to contain but not eliminate. In other words, but each one of these have different factors. For instance, the one right here, is standard GM. Whoops, sorry, back up. That particular unit there, if you put that on a race car engine, you've just screwed the pooch. All you've done is put 10 pounds on this front snout, and it's just useless. Then you have the aftermarket manufacturers, like in this case, ATI or Fluid Damper. Those guys have two different approaches, but both of them have merit. The one that the dampers that are from ATI are very fine-tuned, or within about 50 hertz of frequency, so they are tunable. Now, it's an important part of the equation, because as you make different power, as you use different materials, you have a intercept, again, a problem with excitation. These units are there to try and capture. I'd love to say they sequester, but they just sort of slow it down, right? And what they're doing is, and doing that is they're trying to eliminate this problem right here. And this is basically the front post of the unit, and you can see friction welding. Now that's because the free end of the crank with the dampers out there trying to do its job, and this monster back here, you're making all this power. They're in argument. So you get what, I was sorting it up, just simply call it friction welding. In order for that to take place, you have to get to in excess of 1,500 degrees Fahrenheit. Now wait a minute, your water temperature was X, right? Your oil temperature, right? How did that get that hot?
Friction.
Friction, there you go. That's that simple. All right, so as we moved on with these, now we tried, the worst thing you could do now is take a damper. If you don't know the actual interference fit, you're already making first mistake. You need to know that. And the reason is if it's too loose, it's useless. If it's too tight, it deforms. If it's a fluid damper type application, it distorts, then the inertial ring that's inside will lock up. So everything bad about this thing. So, but what I'm getting to here is this is old school, all right? So as you guys are making all this power, I want you to understand we're having to go back and take another look how cranks are designed. Now this particular one, in other ways, we used to have what we called an interference fit only. We used to have one that had a keyway for timing reference. Then we went to blowers and we were twisting the snout, so we put a double key in there to act as a third support. Well, this is the way it should be. In other words, the spline, because of the increased surface area, is able to spread that load uniformly and basically work up to a limit of power. In other words, there is no perfect world. But here's what's wrong with this. Notice the distance from the bearing to the end of the post. All right? What happens here is these dampers, or blower pulleys, however you want to put it, just think of a flagpole in the wind. And these things are banging, you're hearing the flag clang against it. So is that. It's actually hostile. And guess what it's doing? It's setting up a new exciting impulse. Once again, that transfers through the whole system. All right? So let me bring you future. Notice this one's a little bit different. Notice these holes right here. We're actually bringing the damper that was way out on the end, and we're bringing it up close to the main. We no longer want to have it hanging out in the breeze. Now I'm going to give you another example of that because I'm going to show you a visual correction right here. Take notice, and I don't know if the picture you can see it real well. Look where the location of the damper is, and it used to be way out here on the end. The damper now, its function has been amplified because it's not being asked to correct for deflection. Okay, so it's back to its primary design. Now even that's another story, and I need an hour on that one. But I will simply say the key, I'm going to back up for a second and say this is where you need to start going. If you're doing this on blowers, I understand. But I'm telling you, when you hang that 10, 15-pound damper out in the breeze, it's not staying on center line, which is an amplification of orbit, which is you've totally disrupted the balance scenario.
So moving this and moving the damper back, I mean, makes sense. You're closer in. Why,
to support.
Why, to the support, sure. I mean, why have we not been doing it? I mean,
naivety. You know, what we like back in the day, they used to have a Ford. It was a 391 Ford, 361 Ford, and the post on this thing, I'm not kidding, it was this long, and they always broke. They put them in trucks and they would snap right at the very front. Well, they started picking up on that slowly but surely to where we are conventionally today. But in the performance market, if you're making, I'm just being brutally honest here, if you're pushing in excess of 1,000 horsepower, you are playing Russian roulette.
So the RY45, I mean, you're designed around this.
Yeah.
If you're in the aftermarket, though, I mean, how can I achieve some of this?
There you go. I happen to know a guy at Rottler who we need to go in and modify. You're starting to see now where guys are putting basically a thrust bearing in the front, and they're trying to help support this part of this thing hanging out in the breeze. But it's also something where you're going to have to machine the block. You're going to have to, this is not your father's Oldsmobile gig. If you're going to make power, you're going to have to wake up and understand we now have to move and take this unsupported load and contain it, harness it, however you want to put it. If you keep hanging it out in the breeze, you're going to break crap and not understand why. Well, I know why. You know, you're doing mission impossible. It ain't going to happen. So, but look, this is just another example. Dan Jessel and Jason Line, what they call the Eagle 8, that design mimicked exactly what I just showed here. But here's the thing that's interesting. This is what I want to have a little fun with. That block is about 12 pounds heavier than the conventional block. 12 pounds. How many racers like heavier products? Very few. But they understood that the load generated has to be contained, and they're doing it with mass. Now, mass also is a great dampening device. All right? That's all there is to it. So that wasn't their motivation. Their motivation was they were seeing the mains walk and just move around. And I showed you the picture of the bearings. If they will stop walking, then you're going to have better life because it's doing what its design function was. As soon as it distorts, how is it going to get better? It's a train wreck, right? And guess what? Then the guy says, well, let's hang another tooth on the blower, or let's add a little bit more mixture to our fuel, or however you want to go about it. That block was designed for X amount of load. And performance guys just say, let's run it till it breaks. That's not a good philosophy for me. But in this case, Dan Jessel, when he got involved with this thing, he knew darn well that power is only going to continue in this direction. So we think there's a big difference. Now, let me just go back. Here's what some guys are doing. They're just shortening the snout and pulling it back. I'm not in disagreement with that. I'm just simply saying you're running out of real estate, and it's really a poor way to actually hold that damper. Let me go back to this guy. Notice how we're capturing here with fasteners. All right, so we're able now to take not just a interference fit to hold it. We're not talking about keyings or spline holding it. We're now doing it through fasteners. And doing so, that load moment moves closer to the main. Okay? So this idea here, I've seen people that go that way. It's called a Mullins post. I understand the intent, but that's sort of a halfway ticket. You're not, as you keep making power, this is going to be a bad idea. By the way, I want to go back real quick when I talk about Formula One. You got to understand every rotating device it has, every one of those rotating components has a damper on each one of those devices. We put one on.
That's crazy to think.
Yeah.
I mean, but I mean, back in the V10 era and that, you're 20,000 RPM. I mean, you'd have some interesting harmonics there too. But
well, harmonics, other than making music, probably not the best thing. The only vibration I ever think that had to benefit was when the Beach Boys said good vibration. That was the only one I ever thought worked. But you have vibration related to mechanical activity, you're not going to get that consistent event. It can't happen. So let me lead to this. One of the things we've learned, especially in the top fuel categories, obviously we've changed the materials, but we've now gone to complete deep depth heat treat. But that in its own right sort of helped, but we were still not getting good life. We were getting somewhere between 3 to 5 runs out of a crank, and we had to throw them in the garbage. Well, now what we've done is we've changed the radius. Now, the radius on that is the 3/16 radius, but the bearing manufacturer, he's not joining in on that. So if you'll see on the picture, we have a conflict right here. Now, this is in, again, a static mode, and I can see it. Guess what happens when you put that under load? It's even worse. This thing actually goes to a cup. Now, what we end up doing is we modify the bearing by shorting. Here's, in this case, contact area. Well, there's your remedy. All right, but this still varies. Here's the interesting thing I got to tell you guys. The guy says, I don't want to narrow this because this is where the pressure is being loaded by way of combustion. You agree? I got to tell you something. We've done this on top fuel, and we are probably 25% narrower right now, and the bearings look better. It's I never expected that.
well, I mean, if understanding that if you're getting a harmonic and you're getting 200 thousandths of deflection in certain I mean,
Yeah.
if the bearing, you would statically you'd say, well, that's my bearing surface. But in the dynamic applications that you're running in, if you're now only load, if you're loading eccentrically or off the center line in any way, then certainly you could. Potentially you could shrink down what your theoretical would be, but you'd actually had a true more effective contact, I suppose.
Well, here's what we don't know. We don't know how narrow we can go, nor are the applications always equal.
No.
So it's a big variable. But here's one of the things that's driving me nuts. What we've done, especially on mountain motor stuff, we're running unbelievably excessive clearance between the bearing and the journal. I was working with a team out of Europe, and they're running 9 thousandths clearance, right? And so I said, I just don't think that'll work. He says, well, the engine's not blowing up. I said, no. It's not blowing up as fast, but it's going to blow up. And here's why. The one thing I know about fluid dynamics is a fluid moving that's meant, in this case, to have an oil film, will run away from pressure. If you think it's going to target pressure, you missed the boat. So what it's going to do is it's going to navigate to the first exit. In other words, it's going to go away from load. And the only thing that saves it is that you've timed enough cycle time in this thing you caught it before it grenaded. It is a bad idea, but they're doing it because there's so much power that the journal is so much deflected. They were getting edging right in the corners here, and they said, wow, it's too tight. And so we're going to give it more clearance. Well, let's go back to fundamentals. I don't know how in the world you think that oil will say, no, I'm going to hang around. I'm going to take that pressure. No, it's getting the hell out of there. It's going to run away. So I'm the guy that looks at this thing, and so I'm going to give one more slide here, and I'm going to say why that can't work. And that is, here's an exploded view of a journal intercept in the radius. You notice there's no clearance here whatsoever, and that's in a static mode. So what do you think? Even then, that's going to rub and scrub, right? Well, now go ahead and put load into it. You think it's going to get better? What you've done is you made a really $60,000 lathe. And you're right there, it's just in the oil pan. That's called a lathe now. And something's got to surrender. The softer material will be the first one. So again, not a good idea, but let me go back for a second and talk about these counterweights. The new way of doing cranks, which has always been, cup guys have known this a long time. For Christ's sake, don't weaken the crank. No, also, don't give it a reason to become unstable. Right? If you know anything about Bernoulli's principle and how airflow works and so forth, you understand that as this thing's moving, dry sumps take care of a lot of these issues, but if you're a wet sump and you're running this thing at higher speed, you're actually, just think of a cake mix. You're just stirring it like crazy. And within the scope of that, it's going to aerate. Right? None of that is a good part, because as that oil is transitioning in an aerated vent, air will compress really quick. Fluid is the resistance factor. By the way, pay attention now to this zero weight oil deal coming along. That's a whole new animal. We'll be doing something, talking in the future about that, because GM has sort of stepped in it, and they're having a lot of issues, but we're still investigating cause and effect. But let me get back here for a second. I'm given 2 remedies of not drilling. One of them is just cut it down in a lathe. The other one is we can clip a corner and rephase the counterweight. And I got to get people to understand that the cranks that are coming in from overseas, I'll try and be polite here, but those boys have a sense of humor and where they put the counterweights. Now, for most part, when, let's say, a supplier here orders this, it's going to be a year before it gets back here. And the supplier is trying to get demand, but he forgot to get in front of design. He should have fixed the design. Those guys will do what you tell them. They really will. But real time, we're seeing cranks that will put them on the machine, and you bring it up, and it's in the air. It's not in the counterweight correction area. It's not even the rod pin area. It's right between them. So we developed software that can go in now and plot this and put a remedy up, just like what you guys have done, especially in the home. You can sit there and look at this cylinder silhouette, and you can comp. In your case, the software automatically comps. It takes care of it. So it takes the mental gymnastics out. That's where we're at. All right, we're taking the mental gymnastics out, and we're allowing you to plot this and find out a solution. And that solution may, by the way, mean don't do it. In other words, not economically sound to do it this way. That's the advantage of this type of software. Now, everybody that's done anything has put heavy metal in. And that's, look, it's just simply that there's not enough room inside of the Crank Bay area. And so we've seen people modify percentages up and down. There's reasons behind everything, but I think a lot of it is guesswork, and the fact that it didn't blow up, they now call that religion. And I'm not in that camp. But I also said there, Steve Morris, fun guy, good friend. He did a situation where he had basically populated the entire counterweight, and then he went out and put a different set of lighter rods in and said, oh my God, I got to cut this down. Well, he has a nice video on what not to do, and that is when you look at the clearance between the radius area of the counterweight and the, in this case, the tungsten, he cut it into the point, and all of them launched. It was, wow. That's the best thing I can describe it. Wow. And the video is pretty interesting. You need to see it. But moving on. Here's our goal in balancing. And you notice on the right, I've got these yellow indicated weights, and they are 180 degrees apart. And I'm trying to get to a state of cancellation. Not unlike when we were younger, we played on a seesaw. Equal weight, equal distance, single pivot, we could hover. Cool stuff. Well, that's the goal. And this is what it would look like on the screen. So it's showing you basically a 180 effect. You're in tolerance, life is good. But guess what? We get them out of phase sometime. And now you'll notice on the right, I've got the unit of weight here, and I got this one not opposed. But look at the center here. And what we call the principal center line of axis is still a constant, but the inertia of mass is off-centered. So no cancellation. However, we weren't able to really see that until we brought this screen into play. And now I'm looking at the left side, I'm looking on the right side, but I'm also looking at the static influence right here in the center. So there's no cancellation. You can see this one is not opposed to that one. So in this particular case, I actually have, 33 grams on this side, 26 on this side, and 17 in the center. So now we're starting to have a better visual of what we think we know is good is not good. Now we have new tools, new software that can come in and help us remedy this. And by the way, it actually tells you where to turn this correct here, and it'll make this one opposite and that one opposite. Software's cool. I think for the most part, we may be at a point of summing up.
Well, I appreciate it. I mean, it sounds, if you were going to summarize it, compared, what's the way that is this the key thing for you going forward, looking out, in the next generation of crankshafts, balancing, engine development? I mean, is it a new way of thinking and a paradigm shift, or?
Well, let me go back to this. I mentioned the machine 1883, the unit that was first built. It's still the same principle. Law of physics are in play here. All right, I can't change that. But what we have done is we found access tooling and software that gives a novice an opportunity to sit there and let it do the mental gymnastics and steer us towards correction for a better object.
And we spoke, Darren shared this earlier, that, a lot of, in his world, the advent of 3D printing, the ability to rapidly prototype, CNC machines in general, being able to copy things and make changes and lateral, as he was saying, it's that technology that's giving him that ability to go and try things that maybe even they thought were an idea 20 years ago, but you just didn't have the capabilities or the time. You couldn't take the risk, per se, might be a good word. Or are you kind of seeing that here with some of this stuff of like, hold on, now we can play. And we can play quickly, or we can look at things and we can try new things, and in a structured way of thinking that maybe is a little more pinpointed around each application?
We've arrived at a position that we know a lot more, but we still have a lot to learn. I'm sorry. That's what's cool about what we do as an industry. We may even get a little cocky. Yeah, we got the best of the best until next week. And then somebody says, what if? And then here we go. So, and by the way, let's sort of keep a play in here. One of the things you guys really want to study is this harmonic event I talk about. You got to understand it's one of the voodoo areas of the industry that you guys need to dive in. You need to be really, when you go to PRI, I want you to spend a lot of time in the damper booths. Go to the manufacturer, have a discussion. Because here's the deal, and I think I can say it with absolute certainty, you don't know what you don't know. And those guys really are a lot better. One damper doesn't fit all. Don't think that's the answer. If you're making more power, or you've got a situation where you made power on an engine, but you made a fairly substantial change. Let's say you went from normally aspirated to nitrous, okay? You think that damper is going to work? Not a chance in hell. It's totally alien. So don't remember what you did is just what you did. Don't think you can take that technology and move it forward when you've changed the horsepower. Totally different animal. So that unit becomes eBayed. It's out on the net somewhere. Don't run it, don't try it. And the reason is you're not harnessing, or in this case, dampening a hostile event. Every engine has its personality. Horsepower and RPM, let's put it that way, okay? Last thing I'll simply say is the 410 guys, they don't run a damper at all. And, I sort of get a little put out by that because I realized that at the end of the season, if that crank hasn't broken, they ask me to say, see, ta-da, it didn't break. And I go find out now they go to church on Sundays, Tuesdays, Wednesdays. That's the only salvation they got because that's just crap. All right. Now, let me tell you why they don't want it. That is, that heavy mass out there generally is a gyroscopic effect. Anybody a pilot in here? Time out. All right, I'm a pilot of 40 years. When I sit there and I line up on the runway and I throttle up, we have what we call a P factor, the prop. And so I'm going to right rudder that thing, and I'm going to sit there and keep the nose wheel on the center line. Now, guess what? When you're in that car, and everybody that's seen the 410 group, great race, fun. Just don't stand in the front. Don't get in the front row with anything to eat. You're going to get 2 part dirt, 1 part hot dog. But the point I'm going to say is when they turn left, right, the gyroscope of the damper says, no, we're going this way. And that's all there is to it. And the force is phenomenal. So now I've told them, I said, yeah, but you pay a penalty on this side. And they said, you don't seem to understand. My goal is to win the race. I do whatever it takes. So that gyroscopic effect is such that the driver cannot respond quick enough. In other words, if you learn as a pilot, we always look downstream. We prepare for the next turn. This guy turns and says, what the hell happened? Well, the deal is that's why they don't run them. Now, let me put it on the backside for a minute because I said, look, you got to have a dampening device in there. He said, yeah, we do. We have a water pump. I said, say it one more time. You got a what? Got a water pump. He says, that's my fluid damper. So this is BS, capital B, capital S. The guys have convinced themselves that this works. It's wrong. It doesn't work, but it becomes the old saying, if you say a lie long enough, it'll become the truth. There it is, right there. So if you're a drag racer, they don't want to run heavy mass, but I'm going to go back to what I said about the blocks. You're not hurting yourself because you make the power to comp the weight. Let's be clear about that. If you think that weight is your salvation, as an engineer, you have to sit there and say a lighter mass takes less power to move. Motivation?
Yeah, easily.
Okay. How about to the part where it can't handle load and blows up? There's sort of a path there. Go ahead. So it just makes sense to understand that if you're making the power, it has to be harnessed. When I listen to Keith talk about geometry boards and how the load on the block, do you think that cylinder board is just staying perfectly like it was in the honing machine? Nada. All right. However, if that block is weak enough and it's making enough power, it's going to exasperate the ability of the cylinder to say what was perceived as round. So light is good, but it has penalty of limitation of structure. And so as I'm keying back to harmonics. I can take this unit here and ring it, right? I can hit that bottle and ring it. In fact, anybody wants to look, I can't see from where you're at, but you can see the harmonic develop, but it bleeds off because there's only a single strike of input. Now, if I continue to bang on this thing, it'll sit there and stay active. Eventually, something has to surrender. So understand the intent of understanding harmonics is a key part of getting stability and thereby durability of your engine. Fair enough?
All right. Well, Randy, it's always a pleasure. Appreciate you coming, sharing what you're working on, what's new, sharing some wonderful details, I think. ZPE Live here at Rottler. Randy Neal of CWT. Pleasure working with you, man.
Well, same here, buddy. Thank you so much.